Audience. My name is Hodan Omar.
And my name is Eline Chivot. We are policy analysts at the Center for Data Innovation, a think tank based in Brussels and in DC. And today I'm speaking to you from Brussels.
And I'm joining you from Washington, DC.
First of all, thank you all for joining us to discuss today how will quantum computing shape the future of AI. Over 200 of you registered, so it's exciting to note that there is such an interest for this topic. To our audience tuning in on our YouTube channel, before we dive into the conversation, there may be some time for questions and answers for our distinguished speakers today towards the end of the event. So please go to Slido as a participant. You can join by using the hashtag QuantumAI to post your questions. And you can also tweet as well using our handle and hashtag data innovation.
So before we introduce our speakers, let's give today's topic a little bit of context. Quantum computing holds the potential to revolutionize how well AI can solve problems by harnessing the power of quantum mechanics. Quantum algorithms, for example, may be able to substantially reduce the computing time that machine learning models need to solve complex problems, like formulating safe nanomaterials, enhancing climate forecasts, and discovering new drug compounds. But what really is quantum computing? How much potential does it truly hold for AI? What AI challenges can quantum address, and what's beyond its scope? And what can and should countries be doing to bring quantum-enabled AI from theory to practice? To discuss this with us today, we've got four great panelists. First, Freke Heijmen, who is the Special Advisor to the Dutch Minister of Economic Affairs and Climate Policy on quantum technologies, and is also the Director of Strategic Development at QTech Delft. Next, we have Joseph Lijken, who is the Deputy Director for Research at Fermi National Accelerator Laboratory, and has recently been announced as a member of the US National Quantum Initiative Advisory Committee. Third, we have Markus Flitsch, who is Chairman and Founder of Terra Quantum AG. And finally, we have Denise Ruffner, who is Chief Business Officer at Cambridge Quantum Computing.
Thank you, Hodan. And now let's start with you. Denise, can you explain quantum computing in layperson's terms and how it relates to artificial intelligence in particular, and what are the current capabilities?
Wow, so that's a complicated question. Quantum computing. All right, quantum computing is a new technology in computing that takes advantage of the laws of physics, and very complicated. There's a lot of development going on in the hardware, but currently the hardware capabilities do not exceed classical computing capabilities. Now, what's interesting about artificial learning and quantum computing is that many things in nature are exponential, and because of the exponentialness of the problems, they are very well suited to the type of problems that quantum computing can solve. And so for that reason, those of us that do AI work are very excited about the opportunity that quantum computing offers us. Now that was very simple. I think some other people on the panel could get very
perfect. Thank you. That's the kind of answer that we were looking for, definitely. Now let's maybe ask you, Joe, if you have anything to add to this brilliant definition.
Yeah, I think I completely agree. It's very early days to understand what kinds of problems are going to be the first sort of killer apps for quantum computing. But there are a lot of people out there are looking at various things, and it's precisely because of this idea that for certain kinds of problems, you get an exponential advantage by taking advantage of the laws of quantum physics. And we don't know yet what that's really good for, especially in the near term. But it almost certainly must be good for something. And there's a lot of research out there that's very active looking at different possibilities.
We'll come back to that in maybe more detail, but I'm happy to turn to you, Freke, on behalf of QTech, but also you're working with the government. Let's talk about some of the main challenges in machine learning that you see quantum computing can address, and maybe you can share with us some areas of machine learning that you know for which quantum may not have much of an impact on.
Okay, yes, I totally agree with the previous speakers. And I think if you look at the mathematics of quantum computing, you can look at it as linear algebra in a very high dimensional vector space. So a lot of data with a lot of variables that are interconnected. And this is, well, that gives you an intuition why quantum computing can enhance AI, because in AI, we're also looking at large data sets and all kinds of correlations in these data sets. And yeah, to go into where I think on the short term or on the shortest term, there could be some enhancement of AI. I think in data sets where you have relatively small data sets with variables that are very much correlated, because that with quantum computers with a limited number of qubits can already do something in the future, because quantum computing, and I think that's good to mention, it's in the early days, as Joe mentioned. So there's a big hardware challenge that we face in scaling up these quantum machines. So we need to look for applications with that can already be run on quantum computers with a limited number of qubits.
Yeah, and actually one potential opportunities for quantum computing to improve AI models lies in the reduction of the amount of data needed to train an AI system. Could you tell us a little bit more about how quantum processing could do this in practice?
Yeah, well, there's one example that comes to mind. It's Boltzmann machines. These are a class of deep learning neural networks that can be trained to learn probability distributions, but they are extremely costly to train. And quantum annealers, which is a sort of a quantum computer, they share some important characteristics with Boltzmann machines. They sort of have the same way to minimize an objective function. So their qubits could work on training these kind of data sets. But it's all in the research domain. So there's a lot of research going on specifically to these kind of topics.
Thank you very much. Maybe I'll give the word to Marcus for one last first round of comments based on what you've heard and what you wanted to maybe share about quantum computing and AI specifically.
Yes. So, I mean, if we start with the major question, what are, main challenges in AI that quantum computing could address? So, modern AI is based on smart algorithms that improve themselves by training. These algorithms require increasingly more data and more processing power. And quantum computers can definitely help with both big data handling and fast processing. Technically speaking, learning to deal with large amounts of data refers to sample complexity, whereas fast processing refers to computational complexity. And in machine learning, we always have to deal with an interplay between sample and computational complexity. On the less training samples we want to use, the more computational complex the task becomes. And quantum computing helps us to overcome this trade-off. I would like to give you one example, because people always ask, and I think it's good to understand for examples. And one illustrative example is a navigation problem. Imagine one would like to find an exit from the maze. And if the maze is complex, trying out many paths will be needed. Each path is a data point for training. On the other hand, with quantum computers, we can try a superposition of paths as a single training point, because superposition and entanglement are kind of two of the basic quantum physical principles which are at work in the quantum computer. And this will allow us, to reduce the amount of data needed quadratically, So that will be very helpful for AI techniques in a quantum environment.
Thank you. So we're speaking a lot about data and quantum algorithms. Denise, what role does hardware play in this conversation about quantum-enabled AI?
So hardware and hardware development is very important. And what I want the audience to know is there's probably over 100 companies and countries out there developing hardware. But in the last week, we've had just a huge, or probably a couple weeks to be fair, we've had a lot of huge announcements. So I think those of you that check the news can see that IBM published a very aggressive roadmap to 1,000 qubits, followed by Honeywell announcing a quantum volume of 128, which is the highest quantum volume announced to date, followed by IonQ out of Maryland announcing a 4 million plus qubit device. So there's a lot of progress in hardware. And one of the things everybody says to me is, when is this hardware going to be ready? And I think that the progress is getting increasingly faster and faster. So I believe there will be solutions in the nearer term than the longer term. I think the hardware will still be noisy, or what they call NISQ, noisy intermediate. But I think that we are getting closer to solutions, and the time to start looking at quantum computing and AI is now.
Thanks. I'd love to dive a little bit deeper into the use cases. So Freke, you spoke a little bit about how small data sets and being highly correlated. Some of the use cases that are showing promise in quantum and AI are areas such as healthcare, the financial sector, and weather modeling. Could you give a few more examples and talk a little bit more about the use cases that will be most promising?
Yeah, well, I give you two examples where we are working on with industry already. One is quantum algorithms for genetic prediction. So the problem with genetic trait prediction is central to the seed breeding industry, which in the Netherlands is very big, like growing tomatoes, potatoes, stuff like that. And we are investigating in what extent a quantum algorithm can improve and accelerate the existing method. And exactly because of this reason that this work is done with relatively small data sets, but strongly correlated variables, we expect that quantum machine learning can bring about a breakthrough. So this is one example, and the other is something we are working with Volkswagen. So and that's the optimization of traffic flows. I think with the example of the maze that was being given, one can imagine why quantum computing can help this optimization of traffic flows. So these are two examples, and yeah.
Thanks. Joe, do you have anything to add to this?
There's, of course, a lot, as you might imagine, a lot of scientific applications that people are looking at. And I think science is going to be one of the early drivers for these technologies, just because there are so many different difficult science problems that people are trying to address. And I think that's also good for these more commercial applications, because if you look at something like difficult optimization problems, in the end, there's a lot of overlap between things people are trying to do. The other interesting thing about the science applications is they're sort of closer to what these quantum devices are really doing. In the end, these are quantum physical systems that obey the laws of physics, and they're doing something. And so it's kind of easier to map a science problem into that than it is, say, to map a traffic problem. But once you've sort of gotten over that hurdle, I think it's easier to find more commercial applications.
Thanks. I understand that one of the reasons quantum-enabled AI can be useful for, say, financial trading is because it uses probability to come up with the distribution of possible outcomes and then predicts which is most likely. Marcus, can you talk about how this sort of approach leads to more accurate answers, and which applications this distribution model might work for and which they might not work for?
Well, so in general, I mean, being myself a quantum physicist and having worked in investment banking for quite some time, I think financial services will be also a very early adopter of quantum techniques. they work already, heavily with Monte Carlo simulations, stuff which is very well known to physicists, and actually it's coming out of kind of that direction. And therefore, there are multiple applications actually for the financial sector. For instance, we work on something which has underlying fast evolving processes, which is good for every kind of area where high frequency changes are required, that you'll find in the financial markets quite often. And coming back to your question more specifically, I mean, it's correct that quantum systems naturally output probability distributions different from classical AI systems. And not only these natural probability distributions can be found useful in financial trading, but also the way these probability distributions can be modified. So that, I think, is very interesting. And quantum AI actually provides methods on how the probability distributions can be shaped depending on the target. For instance, the probabilities of target outcomes can be enhanced also, I think, quadratically faster compared to non-quantum AI methods. So here we see another area where quantum embedded AI is just better performing, and actually, but probably we'll come to that later. I think that is already true today with available technology today. So we don't have to wait for the distant future to adopt this.
Thank you, Marcus. And I think, Denise, you made it clear that also, like Marcus said, it's time now to find those solutions and create them. Not tomorrow, couldn't wait. But let's go back to some of the concrete use cases that Haugen referred to. She mentioned the healthcare sector, the weather modeling aspects. For an less educated person to quantum, could perhaps you, Denise, tell us a little bit more about what that means, how quantum and AI can be applied in healthcare and in the weather modeling?
I wanted to talk detection, but let me talk about healthcare and weather modeling. So anything that is exponential in nature, I think is ideally suited towards quantum computing. When I look at healthcare, there's a lot of different areas of application that we can do. At Cambridge Quantum Computing, we're working on helping some pharmaceuticals do drug screening and how to speed up the process by predicting which ligands or compounds will be active. So I just want to comment on that. Weather is also a problem, I think, that is ideally suited to quantum, but we're not doing it. So I want to comment on stuff that we're doing.
Okay. Joe, did you want to come in also on this part of the conversation on use cases?
Yeah, I think one use case that we haven't talked about yet is we increasingly are using AI in edge computing and distributed devices that are embedded somewhere. We do this a lot in science experiments, for example. And there are these advantages, such as being able to retrain with small data sets is a really big deal, because you've got a device that's doing something. Now the conditions change, and you want to be able to adapt to that quickly. And this, I think, is an area where I expect quantum AI to have some advantage and maybe a large advantage.
Thank you for that comment. Yeah, there's an interesting comment from a participant on Slido. I know we want to bring those in later, but there is some skepticism, and someone is asking if he's correct or she's correct in thinking that there is currently no clear application of quantum to AI, nor any clear idea of how it would be applied in the near future. And this person, who is anonymous, unfortunately, is asking, for your whether he or she is correct. What would you say? Who would like to jump in first? Maybe Marcus? I don't know.
Yes. And I mean, I can start commenting on is there today already kind of sensible technology in place or routine so that you can apply it already today, and that it's not kind of distant future music what we are talking about. Yeah, and I think corporates, for instance, can apply such technology already today. And I think it's important to understand that corporates will not shift, away from their classical IT infrastructure and classical kind of AI routines 100% to true quantum. Yeah, and therefore have to wait the next couple of years until you have a quantum machine which is not so noisy, which has enough good performance. The reality will be that this migration path will cross also some kind of hybrid era, yeah, where you work in the combination of classical high-performance computing infrastructure and kind of, true universal quantum machines. And actually, we as a company have just recently launched a hybrid quantum simulator, yeah, and we make that accessible via the cloud. As we are in Europe, it will also be Gaia X compatible. But coming back to the cloud, so what we do is this is a perfectly simulated quantum computer with a couple of dozen qubits, and as it is simulated by classical HPC, so high performance computing elements. That computer has no noise, so no errors, and the number of qubits it simulates are, high performing. And with what we can simulate today already, you can do differential stuff in terms of AI. Yeah, so we have developed some hybrid quantum algorithms which, at this number of qubits without any errors, deliver superior results on big data management than classical supercomputers could do. So in a nutshell, what I want to say is corporates can start today. The way is via a hybrid solution, and hybrid quantum simulators can deliver better results than classical supercomputers already today.
Thanks, Marcus. And still wanted to stick to the challenges corner in the field of quantum and AI specifically. Quantum computing can solve problems faster than supercomputers. And I know there's enthusiasm around this, but many hard problems like cooling and errors, they need to be solved before we get to widespread applications. And not all problems require a supercomputer to be solved. So there are many unanswered questions, like why and how is a quantum neural network better than a traditional one? So it's good to wonder which tasks are better with quantum computing and which ones are not. And so I'm wondering, what are the expectations that may be overblown? Are there some current near-term, again, tangible applications, as we discussed, that do suggest really broader potential? Or are we trying to combine quantum and AI because we just need more computer power? So some sort of a quantum to boost AI kind of thing. And to answer those lots of packed questions, I'm aware, maybe Joe, you'd like to start, and you'd have a take on that.
So I guess the short answer is probably everything is overhyped, but that's just the nature of our field. But I very much agree with what Marcus was saying about hybrid. I think for the foreseeable future, what we're really talking about is not quantum AI taking over. It's classical AI taking advantage of quantum AI in certain cases where it provides an advantage. And I think that's the space we're really trying to explore now. And there are many challenges just because of the fact that the hardware isn't where we want it to be. But of course, that's the time to start figuring these kinds of things out. And I should say there's this idea of co-design, which is understanding these applications better is also going to help us design the hardware to do a better job in the areas that we think are most promising for near-term applications. And this is a big part of what's going on now. Another thing I wanted to mention in terms of possible near-term applications is people that are interested in generative models with some underlying latent variables that describe something that they're very interested in and is very important for some application. Just the fact that quantum does things differently might give you access to a different representation of something that you're very interested in. And different is already interesting in a lot of these applications. It doesn't have to be exponentially better. Just having a different way of representing some very important set of data in terms of a generative model to me, is already a big step forward that quantum can do for us.
Thank you. And maybe turning to you, Freke, would you, I suppose you would agree with what Joe said, but what would you like to add?
Yes, I completely agree with that. And I also think it's important that these worlds, it's also about connecting communities, like classical IT, classical AI. There's a whole generation of computer scientists working on that. And quantum, it's a new paradigm. It's something different. It's complex. So it also takes time to train people, to get these communities connected. And I think the time to do that really is now, because quantum is coming. As Denise was saying, these near-term NISQ machines, they are increasing rapidly in capabilities and numbers of qubits. So we really need to advance the field and connect classical IT, classical AI, classical cybersecurity with the quantum community.
Actually, can you tell me more, Freke, about something you told me in the interview we did together about QTech, that you're bringing in multidisciplinary experts from different fields of expertise together?
Yes, that's we started QTech in 2013, so already 6 years or 7 years ahead now, and that was sort of the driver to do it. It arose from physics, quantum physics, and building hardware devices. But to get this technology working, you need the entire set. You need computer scientists, electrical engineers, even social sciences for interfacing, stuff like that. And what became very clear working in this field is that it's hard to learn each other's language, because quantum, it's complex. So these people have been working on that by training from their 18-year-old, and that's what they know. And how do you work together with another expert that is very deep into algorithms or cybersecurity with the same level of complexity and depth? So it's also about learning each other's language and working together. And I think that takes time. But it's great to be part of it, because that's where the magic happens, right? When disciplines get connected
together. Yeah, absolutely. I'd still want to have the insights of your insights, Denise, on this part of the conversation on challenges. So would you agree with some people that say that quantum computers won't replace classical computers? Maybe you have a comment also on, I've read somewhere that there's a process called decoherence, which is why quantum computers are more error prone than their ancestors. Maybe you can explain that too.
So I do want to say that a lot of people come to me and say, oh, are quantum computers going to replace every computer on the planet? And no, quantum computers aren't good at Excel spreadsheets. So we're going to still all have probably our laptops. I'd look at quantum computers as another tool in the arsenal of computing. So we have things like FPGAs or GPUs. There are different tools in quantum computing. So there's just different tools available. And I think for those of you that are computer scientists or programmers or trying to solve a problem, it's up to you to then work and choose and define. And I think that's a lot of what Joe is doing, how to best take advantage of what tools are available to solve the individual problem. I think the idea that one day there'll be a quantum computer that will solve everything, no, it won't. Still not going to do Excel, but it may help us in certain areas of chemistry. I wanted to talk about fraud detection, which is something Cambridge Quantum is working on, where when you're doing fraud detection, the data is highly imbalanced, right? There's a whole lot of data, not fraud, not fraud, not fraud, and then there's one little fraud in there, and that imbalance of data makes the data complexity very exponential. So that's something that is going to be really suited to quantum computing. but there's other things that aren't. And so we have to look at it as this very powerful new tool that's coming along. And from there, people like Joe, I'm going to say, and Marcus and Freke are looking at which tools we use to solve which aspect of the problem.
Thanks
Maybe
very
Joe,
much.
you want to add to that?
Sorry?
I was passing over to Joe to see if he wanted to add.
Yeah, I mean, I completely agree. It's not that we're waiting for quantum computers to replace our cell phones, but I think in the long term, by which I mean 10 years from now, even you're going to start to see some very important applications of this technology, and this is why you see so many governments investing in this and so many companies investing in this now, because it's not infinitely far away that we see large impacts.
Yeah. Yes.
And if I may add on this, Joe, actually I also think because I think we have shown now quite a realistic picture of who are early adopters, what will be kind of early applications, and how will it be combined with also the classical supercomputers. But nevertheless, being an enthusiast about quantum tech, I think we are really seeing quantum leaps at the shorter time scale. Yeah. And one very important parameter here, which proves that from a financial or investment perspective, is that it's not only now for governments or academia. So also the professional VCs, the venture capital companies come in, and they have, their fund life cycle is kind of 7 year plus minus. So they do expect severe returns, in a time frame of lower than, let's say, 7 years. So that is a really good indicator that I think we'll see real quantum leaps in the development of quantum computing in the next few years.
Yeah. To add on that, my experiences in the last 7 years, all the expectations were they did better, so to say. Number of investments, number of qubits, number of people, number of startups, everything went faster than we originally thought it would. It's really like a wave that's happening, so to say. So it's going to happen, and better be part of it. That's a bit how we look at it. And also to make a connection, I think like HPC, high performance computing, it may be a good example. I don't use a high performance computer for my daily business, but it is a very important thing in the economy and in society. So quantum computing won't take over everything. It will be it could be an add-on for specific deep computational problems.
Thank you. Hogan and I have been checking Slido, and I have to admit, again, there's a question I'm very tempted to ask because we're still just one final question on the challenges. Someone is asking, how should we account for the environmental toll of quantum and AI? Who would like to answer this challenging question?
You mean like the energy use of computation, data center, etc. And quantum computing, everybody probably knows that you have to cool them down to very low temperatures to get these quantum states. I think it's a balance of the costs and the benefits on the other hand. Like, for instance, one of the killer application may be the finding of a new way to create for food fabrication enzymes to have food growth, and the Haber-Bosch process, which is very energy intensive, it takes 3% of all the energy consumption at this point. If a quantum computer or a hybrid solution could improve this process, the benefit could be larger than the investment in. So that is the way I would look at this challenging question.
Thanks. Anyone else wanted to add something on this? Yes, Denise? You have to unmute it.
Okay. I'm trying to unmute. I'm pressing on my screen. I'm sorry, everyone. One of the interesting things, and I don't have the numbers, but quantum computers do use less energy than supercomputers. I think I did some statistics on the Summit supercomputer, and I think if you were to double it in size, which you need to do to get more compute, you would actually need a nuclear power plant to run it. It uses that much energy. And so when you're looking at quantum computing, yes, a computer may be super cooled, or it could be at room temperature like a trapped ion computer. But overall, there's less energy, and adding 1 qubit doesn't really dramatically change the size of the computer or the energy consumption. And adding 1 qubit doubles your capability. So essentially, it is I would say, an energy friendlier device than a supercomputer is.
Yes, Marcus. Thank you, Denise.
Yeah. Yes, and I would add, I mean, if we take quantum advantage serious, we'll soon come into regions where quantum computers will solve certain problems, thousands of years faster than a classical supercomputer. I don't say that we give a classical supercomputer such a task then, but anyhow, they are much faster in calculating the stuff. Yeah, so very, very fast. So that also then, saves a lot of energy. So I think that thing is, in terms of a net effect, a positive impact, which quantum computing will bring to the industry.
Oh, great. And I think that was very interesting to mention here, because not a lot of people are aware of that. So thanks a lot. Now I will let you then take over for the last part of our conversation before the Q&As with the attendees.
Thanks, Aline. So I wanted to look forward a little bit. So Frieke, you were talking about taking an interdisciplinary approach and connecting communities. And so I wanted to ask, are there opportunities for greater collaboration between countries related to quantum? We've seen nations working together and collaborating on AI development, such as the G7 group, the Global Partnership on AI. So are there opportunities for international collaboration?
Yes, definitely. So this is a deep tech industry, very complex, that runs on ecosystems of talent, of investors, of research, and this is not something any country can do on its own. So it's important to work together. So there are a lot of things going on in this space. For instance, on EU level, so within the EU, there are big initiatives to work on this. You have the European Flagship Initiative, which is more or less an R&D program, but also the Euro QCI, which is more in the communication domain of things. Euro HPC, which will be sort of the hybrid example that Marcus also was talking about, between high performance computing and quantum computing, to develop infrastructures for that. And also on a global level, collaborations start to develop. There is this Tokyo Statement. I don't know if you are aware of that, but that was a statement that was signed between the government of the United States of America and Japan in December 2019. And currently, countries are exploring if this can be sort of a framework for global collaboration in this field between like-minded communities and nations. So yeah, I think it's important to engage in an international collaboration on this field.
Thanks. Joe, do you have a US perspective on this? As I mentioned in the introduction, you've joined the national initiative, so would love to hear your thoughts.
Yeah, so in the US, we have this National Quantum Initiative, which was rolled out a couple of years ago, and it's definitely aimed at US economic competitiveness, and it is a very competitive world out there. But I think there's also the realization that if you want to be competitive, the worst thing you can do is sort of wall off your scientists and engineers from the rest of the world, because then you're only looking at a small fraction of the smart people and the smart ideas. So international collaboration is a way to be competitive in the end. And we're doing that, for example, at Fermilab with our quantum research. We're working with scientists in Italy, UK, Canada, and there's protocols for how you can do this in a way that you protect the kind of intellectual property that we want to protect. But international collaboration is essential, I think, to making rapid progress.
Marcus or Denise, do you have any thoughts on this?
Yes, what I would like to add, I think we all agree that this is a kind of collaborative approach, and we have to develop a kind of a whole ecosystem of that new industry, because also, you know, hardware and software have to play together, and this thing is just so big and disruptive that, you know, we need a lot of players, and we need all kind of hands at work here who can help. Sometimes when I'm just wondering, you know, when I watch what with now all the programs being set up, which is good, which is great, also on a governmental level, to push quantum computing to solve kind of real relevant questions of today. I'm wondering whether we consider startups, whether we give them the importance I think they should have, because yes, a lot of that is happening still in academia, but if we talk about commercialization, I think we just not have to wait on the big corporates and kind of the cooperation with large research organizations. Quantum tech startups must play a vital role in that ecosystem, because I think ultimately the disruption will come from startups. I mean, if you look into the automotive industry, that gives you a very good example. It haven't been the incumbents, the very experienced incumbents, who disrupted their own industry. It were the startups, or especially one startup, which is now a multi-billion company. And I think the same we'll see in the quantum tech space. And I think therefore, especially Europe, where, you know, access to capital and financing is not so great as it is in the US, we have to watch out that we give enough stimulus to quantum tech startups in Europe to grow and make that change happen.
So I want to add to that. I was involved very early formation of the startup program at IBM, and have been involved with startups for many years. And the startup ecosystem has grown from 10 companies in 2018 to probably, I think, 360 now. So what the audience will see is a huge proliferation of startups who want to use their creativity and scientific know-how to get into this industry, provide solutions, provide their expertise, possibly in a specific problem area or in a broad range of problem areas like Cambridge Quantum. But I think there's a great interplay between governments, government initiatives, startups, and just worldwide collaboration. And I think that's a great question for the audience whenever you talk to someone doing quantum, to understand what their ecosystem looks like, because there's a lot of talent out there, and there's a lot of sharing and opportunity, and we need to encourage it as consumers as well as researchers.
Great. Actually, one of the questions we just got ties into this well. So the question is, quantum and AI may have disruptive effects on economic and military supremacy. Should we preview an international governance, say like for nuclear? Any thoughts on this? Anyone want to jump in?
Well, I think this is already on the table at government level, because everybody is aware of the strategic applications that quantum may have. So I would like to look at it in the view of trusted communities. So yeah, work on that with like-minded countries and nations that share sort of the same values, economic and societal values.
Great, thanks. And in terms of the relationship between quantum and AI and kind of national advantage, will the country that leads in quantum computing also lead in AI? Will the country that leads in AI have an advantage in leading in quantum computing? Denise, what are your thoughts on this?
Well, so there are many applications of quantum computing. So I think a country that leads in quantum computing hardware technology may or may not have the software talent to take advantage, or they may. So I think it gets very application dependent. So I look at hardware development as very separate. So whoever develops the best hardware will obviously be greatly in demand worldwide, because everybody's going to want to use their hardware, that hardware on their solution to try to get the most out of their solution. So again, this comes into collaboration and communication and kind of sharing. When somebody has some hardware that's great, we're going to see that influence sweep the world, as we're seeing now with a little bit of game changing from the dominant players in quantum as the competition heats up.
Thanks. I'd love to take some more questions from our audience. So I'll hand over to you, Aline. I think you're muted.
You see, I told you that would happen to me as well. Yeah, it's quite impressive to see a lot of participants have been posting questions, and a lot of our audience seems to actually know quite a bit about quantum. So that's impressive. And thanks for having mentioned the topic of this sort of potential global race or competition towards reaching, well, what we call also quantum supremacy, right? So we'll see how that develops. But there are signals that some countries believe there's going to be a big breakthrough in that field. So let's turn to participants' questions. There's one that I thought would be interesting to ask. Again, back to the challenges. One participant asks, AI currently uses lots of data, and quantum computing is, and arguably always will be, bad with lots of data. Is there any truth to this statement, do you believe? Who would like to start on this provocative comment? Joe?
I mean, this certainly is a challenge just in the scientific applications I was talking about. You know, we can't take all the data coming out of the Large Hadron Collider and put it on a quantum computer. It's just not possible. But this doesn't mean that you can't take pieces of interesting problems and put them into a quantum computer. It was an interesting paper last year by the IBM Zurich group, which was looking at doing a sort of a classical AI processing where you're trying to understand what's the probability distribution of the underlying variables, but the output of that was actually a quantum system that reproduces that probability distribution. So at that point, that's the thing you feed into the quantum computer is represents what you care about in the data, but you're not actually feeding all the data into the quantum computer. So people are thinking of creative ways of getting around this problem, which is a problem certainly for near and medium term quantum computers.
Anyone else wanted to comment on this? No? Well, we have another question, actually I'm just going to take a pack of 3 from Richard Polivka. Thank you for joining us on Slido. You are from AI Consulting. So there's a few questions. I'm going to pick two of them and then direct them to whoever wants to respond. So the first question is, how easy is it to use the hybrid quantum cloud? What is its availability? And the second question is, how many qubit quantum computing can you simulate with the hybrid computer before it gets computationally impossible for the underlying classical infrastructure? So who would like to respond to Richard?
I mean, I can start. I mean, as I think it's referring potentially to what I mentioned earlier, the launch of our hybrid simulator, quantum simulator, and how is that accessible? It is a cloud service, so you can actually access, Terra Quantum's quantum simulator via QMware. That's kind of our product, and you just access it via a web front end, like any kind of other cloud service. What is simulated is the performance of, I said, a couple of dozen qubits. I don't want to go into more detail, but I do think that HPC computers today can simulate in the order between, let's say, 40 to 50 qubits. But that has to be compared not with a 40 to 50 kind of true quantum machine, because the performance is much better because you don't have any errors, no noise. Yeah, so it's much more powerful than a comparable 40 true qubit quantum machine. And that is also why I said that with such a performance, you can do certain AI applications better and faster than on classical supercomputers. Of course, that has and that's why this is kind of a bridge technology that has, some ending. Otherwise you wouldn't have to develop a true universal quantum computer. So this, has some ending, but I think we still haven't seen the end yet. And such hybrid simulators will play a vital role in the next years also to test new algorithms on their performance and to predict when really is the advantage kicking in, because you can simulate that then and see it on this machine. So that's from my side on the QMware hybrid cloud.
Okay, anyone else had anything to add on this particular question?
Well, maybe one thing that we also have a same sort of hybrid simulator available in the cloud. It's called Quantum Inspire. It's for educational and testing purposes. So anyone who would like to access it, just go to www.quantuminspire.com. And then you can test sort of simple algorithms on a high performance computer. So the same what Marcus is offering.
Thank you. That's very useful input. I have one more question for you, and maybe Hoden, then you can ask another question from our participants. S. Jones is asking us, assuming quantum computer does not depend on traditional computing hardware, might quantum computing provide opportunities to leapfrog Moore's law limits with silicon germanium-based semiconductors? I told you they were very well informed. Who would like to take this one?
Maybe repeat the question again, like the Moore's law, the end of Moore's law in silicon for classical computing.
Yes, so I will just read it again. Assuming quantum computing does not depend on traditional computing hardware, might quantum computing provide opportunities to leapfrog Moore's law limits with silicon germanium-based semiconductors?
Mm-hmm. Well, I think that's one of the reasons that this field is growing so fast, is because of these limits, that we're just coming to the limits of what is physically possible on the number of transistors on a chip. And this is a reason why we are looking at these new quantum solutions. And there are several paths being taken. So ion traps were mentioned before. We are working with germanium, silicon, superconductors. So yeah, I think it's a broad field of new solutions just to get over this limit that Moore's law proposes.
Great, thank you. Thank you for addressing that question. Hoden.
Yes, we have a question for you, Joe. Are you collaborating with the European Organization for Nuclear Research, CERN, and if so, in which direction?
Yes, thank you. So indeed, my lab, Fermilab, and CERN have been collaborating for 20 or 30 years now. So we have actually, at the moment, probably 150 of our physicists working at CERN. So that's a collaboration that started with particle physics, but we have been having discussions over the past year or so about collaborations on quantum technology. And it's because of the realization that this quantum technology might be useful for our science that we do at both these laboratories. So I see that as a growing area of collaboration now with CERN.
And we also, Cambridge Quantum has a collaboration with CERN as well, where we're working on Monte Carlo algorithms, as well as to help interpret their data, as well as some quantum random number work. So we're quite excited to be working with CERN as well, although we don't have 150 scientists there like Joe does. So Joe, you got us beat there.
For now.
For now, that's right.
We have another technical question, and if you could break it down for those who are policy-minded, would it be correct to say that the greatest benefit of quantum-enabled AI is to explore the function minimization space more efficiently in order to avoid local minima? So if anyone would like to explain the question and then explain the answer, that would be great. Maybe Joe? Or...
I think I can explain the question. So everybody has some kind of optimization problems where you're trying to find, the best solution to something. And part of the way you turn that into a quantum computing problem is you take a quantum physical system and you map that problem into finding the lowest energy state of that quantum system. This is in some sense the way that D-wave computer works, for example. So this is something that we understand from a physics point of view very well. We understand why it's difficult, because for very many physical systems, there's a lowest energy state, and then there's millions of other states that are very similar to it. And so it's very easy to get trapped in the solution that isn't the best solution. And how do you escape from that and get to what you're really looking for? So this is a very general problem, and it's one of the reasons why we think that these quantum hardware might have very general applicability, because if you find it turns out to give you an advantage in some particular application like this, it probably means it applies to many other applications.
Thanks. I think that was able to be followed along, so thank you for that. So one question I'd like to pose to you all as our final question is on workforce development. What specific areas should we be focused on from a workforce development perspective to stay competitive? So Frieke, I'll start with you.
Well, this is a topic very close to my heart. If you ask me, I think this panel today also illustrated this. It is complex. It is really complex. Quantum computing is complex. AI is complex. The engineering is complex. And up till now, it has largely been the domain of very high-skilled PhDs and professors. And I think if we want to scale this technology, we also need a workforce on all levels that can work with the technology. And not everybody has to write a physics paper in Nature or, answer questions that came up today, but people need to work with the technology. So I think we really start thinking about programs, educational programs to teach the entire chain of talent that we have.
Thanks.
And I'll add to that. I think there's a lot of education programs out there. I would tell you, before you pay, look at the free programs. There's a lot of really great free programs. There's a lot of programs if you have a kid in high school or a younger child that want to look into quantum. There's a lot of programs that start at high school or kind of early teens. And there seems to be some real talent in picking up the quantum programming and quantum theory. So I encourage everybody to reach out on the internet, look at all the different education, focus on the free education to start out. And that's just a great way to get started. There's all sorts of hackathons and programs. There's some through CERN actually, and in Switzerland. There's all sorts of stuff out there. I'll also mention there's a website, I'm going to do a little ad here, called Quantum Appalooza, that lists all the seminars that happen every day in quantum. And so if you want to just go to a seminar and learn a little bit more about quantum, it's all free seminars. So I encourage everybody who's taken the time to listen to us to take a little time and look at the internet and look around at what there is. Don't pay. Take some free classes, take some free seminars. There's a lot out there. You can gain all the knowledge you need through these seminars and education.
If
Wow.
I
Thank you.
if I may add, also my little kind of marketing campaign for quantum physics, not for my company, but for quantum physics. I really think, I mean, deep tech, has become amazingly attractive. I think quantum physicists are really the new rock stars. I think we'll really see a shift, of interest, because it has such, massive implications in the next decades. I do think, quantum physics has become very, very attractive, and a lot of people are getting more and more interested. And I think we need more of these people, actually, because there is a talent shortage in that industry, definitely. So we need more of them. And, I'm very happy to have heard that, there are several people in that panel who have connections, and also I think in the audience, to CERN, my alma mater. I, studied at CERN kind of 25 years ago. But I'm very happy that, research organizations, also like Fermilab, of course, but in Europe, CERN, are great organizations where people can learn and are getting educated, and then, help us in building the quantum tech industry. So I'm really looking forward to that.
Thank you, Marcus. I think your enthusiasm is contagious as always. And I think it's time for us to wrap up. And Hoden, I don't know about you, but I think I felt I was in very impressive company. So thank you so much for sharing the hour with us, to the four of you. We've covered the convergence of quantum and AI and how quantum relates to AI and the main challenges as well, and the areas that were promising. But we also discussed, how can that move forward in international governance. Now, thank you so much again, everyone, for tuning in with us today from Brussels, DC, and everywhere else. Our warm thanks go to our distinguished and excellent speakers. Again, we hope you've enjoyed the conversation. We're looking forward to connecting again with you soon. Our next events will include a book talk on the reasonable robot, AI and the law, with Ryan Abbott on November 13th. And we'll soon announce the next panel, which will be about the EU's Digital Services Act, or more or less now Digital Markets Act proposals regarding large platforms, market power. So stay tuned for more. There is a lot going on. And thanks again so much, everyone, for your time. Bye.